Hello. So last time we had seen how to evaluate the partition function of um, a monoatomic ideal gas. And let us take this further and see how one can do for a diatomic molecule. Again, ideal gas, of course. And that's where we'll stop. And we'll not evaluate any more molecular partition functions. The idea of this course is to give you an insight into how one can essentially evaluate these or one can deduce these molecular partition functions, and from there go ahead and look at the thermodynamic properties. This is just to give you a flavor. So the partition function Q, which is a function of capital N, capital V, capital T, the amount of the substance, volume, and the temperature. We've seen already it is given by the molecular partition function, small q, which is a function of the volume and the temperature raised to the power n by factorial n. Now, factorial n because we are dealing with identical particles, non-interacting particles, and we are dealing with indistinguishable particles, right? So this is what we are going to use. And we know that this total energy, so we are going to use the harmonic oscillator rigid rotor approximation. So under this approximation, I know that I can have all my energies separated out. So the total energy happens to be a sum of the translational, rotational, vibrational plus the electronic energy, and therefore the partition function, the molecular partition function, can be written as Q trans multiplied by Q rotational multiplied by Q vibrational multiplied by Q electronic, right? As it's given here. Now, for the case of diatomic molecules, we're going to look at each of these contributions to the molecular partition function one by one. Okay, I don't need to do for the translational one because we've already done it. The only difference that you'll see in case of the monoatomic molecule versus the diatomic molecule is the introduction of capital M. Now, capital M happens to be the total mass of the molecule. Right? So, you could also take both of these atoms and make them translate and see what the energies come out to be. So, just need to add M1 plus M2. Okay. So, it's exactly like the monoatomic molecule, 2 pi M by beta H cross square raised to the power 3 by 2 multiplied by the volume of the system. So we have the translational partition function for the diatomic molecule given by this particular equation. All right. Okay. Now, before I go into the rotational, vibrational, or electronic partition functions, for each of these cases, right, one has to worry about the zero of energy. So I have to worry about the zero of rotational energy, I have to worry about the zero of vibrational and the zero of electronic energies. Okay, it doesn't matter if I choose different zeros for all of these different systems, because all I'm going to do is to fill up these levels, right? I'm either going to fill up or account for, not fill up, but account for the rotational level separately. I'm going to account for the vibrational level separately and the electronic level separately. So it really doesn't matter if I choose different zeros of energy. Okay. So let us look at the rotational zero of energy, and that's very easy to choose because when J is 0, E is 0. E is nothing but J into J plus 1 H cross square by 2I. Yes, this is something you should remember from the quantum mechanical part that we've done a few days back, right? So Ej is equal to J into J plus I into H cross square by 2I. Yeah, this is one of the equations that I definitely want you guys to remember. So the rotational energy is 0 when J is 0. Let's use this as the reference of rotational energy. Okay. What about the vibrational energy? Where do we choose? Well, before we do that, let me show you this particular curve over here. Just look at the bottom curve. Okay. The bottom curve tells you an so this curve is for an internuclear potential. Okay. So this is the electronic ground state of the two nuclei that are coming together. You have energy on the y-axis and the internuclear separation on the x-axis. Now, there happen to be two things over here. Look at this dE, equilibrium energy, and D0, the dissociation energy. Okay, which one do you want to choose is the question. One could choose anything. As I said, you could have any reference of energy. For the vibrational state, what is it that you want to choose? For the vibrational state, what is normally chosen is the ground state vibrational energy. Okay. What we take is that the ground state vibrational energy should be equal to h nu by 2. So, this particular, the lower part of the curve happens to be 0 for the vibrational energy levels. Okay. Again, as I said, you can choose anything. It's not going to make any difference. But there are some norms which books are following, so let's follow those norms. We choose this point as the 0 of energy for the vibrational levels. So your lowest ground state, ground state energy happens to be h nu by 2. Okay. And what about the electronic ones? Yeah. What I've written over here is most molecules in the ground state. And we'll just see this. What about the electronic energy? In case of monoatomic ones, what we chose was the lowest energy to be the ground state energy that was chosen as 0. For example, minus 13.6 for electron volts for hydrogen, I could choose as 0. Whatever is the lowest energy. In case of the molecules, it is more advantageous to choose this 0 of energy. This 0 of energy is when the two atoms are completely separated. Alright. So when these two atoms are completely separated, then there's no interatomic interaction, no bond, nothing, and that is the 0 of energy. Okay. If that is chosen to be the 0 of energy, then the minimum of this curve, which describes the bonding situation, happens to be at minus dE, d equilibrium, right? That's your equilibrium bond length, and that's the energy, equilibrium energy. Okay. Remember, because of the vibrational state, the molecule would be sitting over there. The lowest energy would be there, and when it has to dissociate, it is going to require an energy of D0. Anyway, so now what we need is to describe this ground state for the electronic energy levels. And if I describe this minus dE as the ground state, then the Q electronic, the partition function, the partition function is nothing but sigma G, which is the degeneracy, e to the power minus energy by kT, right? So minus energy would give me plus dE. Okay, dE happens to be a positive number here. All right. So that would be my ground state, the contribution from the ground state to the partition function, and then the contribution from the excited state would be whatever that excited state energy is multiplied by the degeneracy, e to the power minus excited state energy by kT, and that excited state energy, whatever that epsilon E2 is, again that would be the bottom part of the excited state curve. And don't worry, this excited state curve could look like this, it could look different from this. It really depends on what system and which particular excited state you're looking for. So let's not worry about that for the moment, but whatever it looks like, this lowest part happens to be the energy of the excited state, right? If I had taken 0 over here, then the excited state energy would have been dE plus epsilon E2. And if I were to look at the contributions, the ratio of the contributions coming from this term, that is e to the power dE by kT, to this term would have been exactly equal, right? If this was 0 and this was dE plus epsilon 2 instead of epsilon 2 and dE over here. So there is absolutely no difference in the occupancy, or in not just the occupancy, in the number of energy levels that are available. So that will not make any difference, whatever reference of energy that I choose. Okay. Now, if you look at the energy difference, right, dE happens to be on the order of a few hundred kilojoules. These are typically bond strengths. These are on the order of a few 200, 400, 600 kilojoules per mole. And the vibrational energies, they are only a few tens of kilojoules per mole. Okay. So now if these are going to be 100 kilojoules per mole, everything is going to be in the ground state. We have seen this in the previous lecture also. So I really don't have to worry about the excited states at all. Okay. We'll see that later also. And if you think of the difference between D naught and D, then it's a few tens of kilojoules per mole. So it could be 20, 30. It depends on the system, of course. All right. Now, let us, having learnt about the energies and the energy reference, actually, let us go ahead and evaluate some of the components of this molecular partition functions. Okay. So now let me look at the vibrational partition function for the diatomic molecule. And again, what I have written over here is, you'll see most molecules are in the ground state, but there are some molecules in the excited state. Yeah. When I'm dealing with energies of 10 kilojoules, when I'm dealing with 100 kilojoules, then absolutely everything happens to be in the ground state. When I'm dealing with 10 kilojoules, then of course kT is not so low, kT is comparable, and things do go in the but most molecules still are in the ground state. Okay. So I know from the harmonic oscillator approximation, I know that the energy, the vibrational energy, is given by V plus half h nu, where V goes from 0 to infinity. Right? And if I were to calculate for the molecular partition function for vibration, right, which is a function of temperature, okay, it does not depend on anything else, and then it's nothing but a summation over all these energies. So e to the power minus beta over all these energies, beta EV. Okay, so these are the EVs. I expand that, right, e to the power minus beta V plus half h nu, and I see that minus beta h nu by 2 can be taken out of the summation. So it's just e to the power minus beta h nu v, which needs to be summed up. Okay. Now, this happens to be a very nice geometric series, e to the power minus x. Okay. V, yeah, or I could just say x to the power v, or yeah, x to the power n. So summation of x to the power n is 1 over 1 minus x, given the fact that x is less than 1. Okay, only then this summation holds true. Okay, so this is one thing. If anybody is more interested with the series part, this is also given in Macquarie, in one of those interludes between the chapters. I think this is the one just before the diatomic molecular partition function chapter. Okay. So if I were to use this formula, then what I get is the molecular partition function for vibration comes out to be e to the power minus beta h nu by 2 divided by 1 minus e to the power minus beta h nu, right? So this part is coming from the summation, and this part was the numerator comes from here, what had come out of the summation. I can also write this in a slightly different fashion. I could write that e to the power minus beta h nu by 2 is essentially e to the power minus h nu by 2 kt. Okay, so h nu by k happens to have the dimensions of temperature. Okay, so yeah, so I could call that h nu by k as a theta vibration, a vibrational temperature. Let's call that. Okay. Well, what it essentially means is that this energy level corresponds to such a temperature. So if I were to multiply that temperature by k, I would get the energy level. So yeah, vibrational temperature theta is h nu by k. Okay. Now I could also calculate the average vibrational energy that comes out. Okay. In fact, yeah. So if I get the average vibrational energy, I know the formula for average vibrational energy is minus d log q by dt. Minus d log q by d beta, which I can convert to, from capital Q I can convert to small q, and from beta I can convert to temperature. But it's always good to work with beta. Your life is much easier, and then later on at the end convert to temperature. So what we get is nkb theta by 2 plus theta by e to. Remember, this is the theta by 2, and this theta by 2 doesn't have any, it's just h nu by k. Theta vibration is nothing but h nu by k. And then k gets cancelled with this particular k. Yeah. So this is nothing but h nu by 2, which is the 0 point energy. And this is the energy due to the states that get filled up with temperature. If I were to plot, well, no, I have not plotted this. I have plotted the CV, which is nothing but change of the energy with respect to temperature. What I get is theta by 1 minus e to the power minus theta by t whole square, and that's what has been plotted over here. If you remember, this form of the curve is also something which you see for the heat capacities of solids. Well, although the partition function is slightly different from what you have over here, but definitely it's of a similar um, functional form. That was also vibrations, yeah? That was vibrations of solids. And it's given in your tutorial, which you need to do also. Okay. So you have vibrational contribution to the molar heat capacity is given by this particular equation. There's something more important, that you can estimate what is the fraction in the Vth energy level, Vth state. So that is nothing but e to the power minus beta h nu, right? That's kind of a probability, yeah? E to the power minus beta h nu into V plus half by Q vibration. That's the fraction of molecules that would be present in the Vth vibrational state. Okay, and you can reorganize this equation and write as 1 minus e to the power minus beta h nu. Okay, and you can bring in the value of Q vibrational from here. Okay, and what you get is 1 minus e to the power minus theta vibrational by t, e to the power v theta vibrational by t. So another important thing over here, what you can calculate is the fraction that are not in the ground state. So the fraction that are in the excited state. So Fv greater than 0. That is the fraction in the excited state. So all you need to do is to count for v is equal to 1 to infinity f of v, or what you can also do is to just account for 1 minus f0, and f0, just put the value of 0 over here. What you get is 1 minus e to the power minus theta vibrational by t. V comes out, v is 0, so nothing, so e to the power 0 is 1. 1 minus f0, so that is just e to the power minus theta vibrational by t, or e to the power minus beta h nu, or e to the power minus h nu by kt, or e to the power minus delta E by kt. You're well aware of the Boltzmann distribution. Yes? Good. Now what you have over here are some values from the book. If you look for some of these gases, for example hydrogen, the vibrational temperature is given by 6332. These are all from harmonic oscillator calculations. Remember, hydrogen will not show you an IR band, but it does vibrate. Okay, so it does have vibrational energy levels, and therefore it will have a vibrational temperature also. The fraction that is occupied in the high energy states is very, very small for 300 Kelvin, also very small for, sorry, this should be 1000 Kelvin. Okay, so for 1000 Kelvin. This is nothing but, look, the fraction v greater than 0 is nothing but e to the power minus theta by t. And if I look at that, if my theta goes down, so should this fellow increase. Okay, so if theta goes down, this fellow keeps on increasing. Also here, some of them I have marked in yellow because these seem to be not following the trend of theta, so I'm sure these are some misprints in the book, but one doesn't have to worry about that. What one has to worry is that as theta goes down, well, of course, so you're going to lower and lower temperatures that correspond to the energy separation. So if you're stuck at 300 Kelvin and you go from gas to gas, and where your theta is going down, so more excited states are likely to be occupied. Okay. Yes, for iodine, more excited states are occupied than for chlorine, than for hydrogen. Okay. But if you look for most of them, well, iodine is a very heavy gas, yeah. Otherwise, if you look for that, if you look for chlorine typically, and these are ordinary temperatures, 300 Kelvin. Yeah. So if you're looking for nitrogen, for example, it's barely a small fraction of the gas molecules that are in the higher excited vibrational states. Most of them are at the ground state, at ordinary temperatures. Yes, when you are at higher temperatures, then a few of them do go to the higher excited states. But at ordinary temperatures, most of them happen to be in the ground state. Okay, good. Now we'll go on and see how do we account for the rotational partition function. Okay, and if I may already say, and I'm sure you would have guessed that too, that most molecules are in the excited states at room temperature. Remember, the rotational energies were 100 times, I think, much smaller than the vibrational energies. Okay. So the energies are given by h cross square j into j plus 1 by 2i, and the degeneracies are given by 2j plus 1. So Q rotational is simply sigma j is equal to 0 to infinity 2j plus 1 e to the power minus beta h cross square j into j plus 1 by 2i. Yes? And let me at the very outset define the rotational temperature, which of course I can see from here. I don't need to involve the quantum number. All I need is leave out the quantum number and leave out the temperature. So h cross square by 2i, beta is 1 by kt. So h cross square by 2ik. That's it. So h cross square by 2ikb. Okay, which I can also write as h into b by kb. Remember b was the rotational constant, h squared by 8 pi square i. We've seen this. This usually is much lower. This theta rotational, the rotational temperature, is much lower than room temperature. Okay, if it's much lower, then I know that the higher energy states should be occupied. Right. Now, if the fact that this rotational temperature is much smaller than the temperatures that we are evaluating the rotational partition function at, then instead of writing a sum, I could go over and write a integral. Although this is an approximation, but I can do it. If these are very closely spaced energy levels, then I can just integrate. And this integral is very straightforward. I could do these small substitutions over here, and I can get my integral to be t divided by theta rotational, which is nothing but 8 pi square I kbt by h square, which is equal to 2 I kbt by h cross square. And then of course I can use this Q rotational to get the rotational energy for the entire ensemble. Yeah. For the collection of molecules, you see, I have the capital N over here, so it tells me it's collection of molecules, and I'm using the molecular partition function over here. Okay, so which is T by theta. Theta happens to be a constant, remember that. So dt by dt, nothing else. So nkt. Okay, that's what I get, which is nothing but RT for 1 mole, or CV, then molar heat capacity for rotational comes out to be R. Fj, now like we had Fv, the fraction of particles in the jth state, can be easily evaluated likewise, and here I have a formula for that: 2j plus 1 e to the power minus theta rotational j into j plus 1 by t divided by q rotational, nothing, right? This is nothing but this fellow divided by q. Okay, and q I already know, it's t by theta rotational, so I can put all that and get Fj. And since I get these values, I know that most molecules happen to be in the excited state. Now, something very interesting is to find the most probable state in terms of occupancy. When you're doing spectroscopy, then you're looking for transitions. Remember, delta J. Delta J is equal to plus minus 1 is the selection rule that you got. Now, if delta J happens to be plus minus 1, and if you don't know about the occupancies, then you do not know which particular line. Remember, we had a series of lines. We had a series of lines in the rotational spectra, all separated by this rotational constant 2b. Right? The rotational constant 2b. So we had a series of lines. Which of these is the most intense? Okay, that will be given. Well, we are under the rigid rotor assumption. Okay, so we are not changing that. So that will be given by which particular state is most occupied. Okay, and that will depend on the temperature. So I can actually treat this as a continuous variable, and then do a df by dj is equal to 0, and I get most probable j. If I do that, df by dj, I get t by 2 theta rotational to the power half minus half. All right, so I can get the state which is most populous, and if I know that, then I know that the maximum number of transitions are going to happen from that particular state. So I know which is my most intense transition line. All right. Now, in case, see what I've written over here is something usually. In case it so happens that your theta rotational is not so small in comparison to the temperature, of course. So small molecules, for example, hydrogen, they have a theta rotational of 85.3 Kelvin. It's not very small. It's small, but not very small. Then in that case, it's not advisable to use the integral, but you can use the sum over here. But remember, as you go to higher and higher values of j, contribution is going to be small. So the first 3 or 4 contributions are more than enough in order to estimate Q rotational in these cases. Okay, but don't worry. For this course, we'll use only the high T limit, which means we are going to use the results of the integral only. So we are not going to worry about summations. There's another thing which is called the symmetry number, which is required in order to account for the different rotations, especially when you have homonuclear diatomic molecules and the orientations of rotations get doubled up. But for this course, we'll just not worry about those details. Okay. Those who are interested can always read my query. Now I come back to something that we did in the first lecture of the thermodynamics part. I had given you the partition function. I had given you that the partition function was q to the power n by n factorial, where the molecular partition function was given as 2 pi m by h squared beta to the power 3 by 2 times v, the yellow part, which now you can recognize is because of the translational part. Okay, 8 pi square I by h square beta, which you will recognize is the rotational part. Yes, you can see this is t by theta, and theta is h b by kb. Yeah, or if you want in terms of 8 pi square I by beta h square. So this is what we were looking for. And the blue part is the vibrational partition function. So this is what I had given you in the first lecture. I had asked you to use it, and by using it you had calculated the average energy, which was 3 by 2 RT for the translational part, RT for the rotational part, h nu by 2 for the ground state energy, the ground state vibrational energy, and this term for the energy that comes at higher temperature from the population of the vibrational states. Right. The rotational states, all the states are populated, so you just get RT. Doesn't matter if you have higher energies, then also all the states are populated. So for translation also, continuum of states, that's a continuum of states. Here we have discrete states which get populated, but always the ground state is always populated, so that's a constant one. And this is what changes with temperature. And from there you had also calculated the heat capacity. Okay, so we'll stop here. But before we stop, let me tell you that this concept of deducing the molecular partition function can now be taken over to polyatomic molecules. But of course, there are many more concepts that will come in over there, and we've not studied those things, so I would rather refrain from getting into those details. But what I wanted to give you was a flavor as to how one can account for different terms over here and different contributions, and essentially derive all these molecular partition functions. So once you know these molecular partition functions, you can of course go ahead and derive all the properties. So in the next lecture, we'll go on and look at some of the properties. We'll start with the first law of thermodynamics. I'll go very quickly with the classical part, because that is something, I'll give you some questions also, some extra questions to practice. But what I would like to show you is how does the knowledge that we've learned now, how does it help in understanding of the thermodynamics. Thank you.